Thank you, everyone, for staying this late in the day. Is it OK that I speak English? All right. My name is Sergei Sokolenko. I'm a PM, product manager in Google. I work from the Seattle office, and I work on cloud Dataflow. That's Google's streaming analytics product. And I'm also involved with the Apache Beam project, part of the Apache Foundation. So today we'll be talking about different options for streaming processing in the Google Cloud and in general. And then I'm going to show you a demo of how Dataflow is doing streaming analytics at Google. Just a quick show of hands. Who knows what streaming analytics is? All right, so it's maybe 50% of you. For the rest of you, I do have some introductory slides, so you'll be able to learn more about streaming analytics. And for those of you who did raise their hands, I do have some new stuff here as well, so hopefully it will be interesting for everyone. So the session will be structured into, let's do an overview, and then let's dive deep into lessons learned, lessons that Google learned by building a streaming analytics service in GCP. And lastly, we'll do a demo. Google Cloud is available in 20 different regions. I thought I would do an introduction of the Google Cloud. Some of you might not be aware of what it is, what we offer. So we are present in 20 different regions across the world. We have a very fast and very powerful and high-performance network. Some say that this is the kind of one of the better qualities or best qualities about the Google Cloud, our networking. So it connects through thousands and thousands of miles of fiber across oceans, all of our data centers. And we have direct, dedicated interconnect pretty much in every major city in the world. Moving over to what we offer in terms of services. I only have a slide for big data. So the entire range of services, starting with virtual machines and going to storage and doing databases, relational databases, NoSQL databases, that wouldn't fit one slide. So I decided to just do a big data overview slide. In terms of big data, what we offer is the full range of ingestion, streaming analytics, data warehousing, advanced analytics, including ML, as well as some horizontal services. For example, Data Fusion is a ETL tool, and Cloud Composer is a orchestration tool. If you are familiar with Airflow, then Composer is managed Airflow. Now that we know a little bit more about the Google Cloud, let's actually talk about what Google did in terms of data processing. As you can imagine, Google has a lot of bytes to process. Think of Gmail, think of Google Search, YouTube. All of this data needs to be processed to be useful. And so very early on, early 2000s, Google has published several academic white papers on how to do large-scale data processing. So the first paper that was really successful was MapReduce. We wrote this paper, and it became the basis of Hadoop, Apache Hadoop. It was also offered across pretty much every cloud provider. Everyone runs Hadoop in their environments. So that was very successful. But then we realized MapReduce can be quite daunting to use. It's not a simple way of expressing data transformations. So then came Floom Java. And Floom brought this idea of, let's not talk about maps and reduce functions. Let's talk about what is the graph, what is the data processing set of steps I want to do to my data. And this basic idea became also very powerful and popular. Lastly, on the streaming side, Floom was batch. On the streaming side, we published the Millwheel paper, which became the basis of many, many other streaming processing frameworks. The combination of Floom Java and Millwheel became Cloud Dataflow. It was our external user-accessible service. We launched it in 2015. And two years ago, we open-sourced our SDK, and it became the Apache Beam project. It's actually a very popular and very well-used project now. The second year in a row, Apache Beam was rated one of the top 3 most used and most popular development frameworks. That's statistics published by the Apache Foundation. 2 weeks ago, we finally deprecated the last line of code related to MapReduce. This is my Uber boss, Urs Hurlsle. He's been with Google for 20 years now. He was the guy who, I guess, invented MapReduce, or at least he paid for the creation of MapReduce. And 2 weeks ago, we completely eliminated the last line of code related to MapReduce. Instead, we now offer things like Dataflow. Let me just explain why we had to do what we had to do and move away from MapReduce. If you look at your typical transforms that you use in MapReduce, you have the mapping functions and you have the reduction functions. And then you're trying to map your key value pairs between the 2 stages. Some of the Google pipelines that we used at YouTube and Gmail, they had 116 stages expressed as a MapReduce relationship. And as you can imagine, that quickly went out of hand. So the Floom Java idea actually brought some standard computer science concepts, such as direct acyclical graphs, DAGs, direct acyclical graphs. And they're nothing else but a way to express your steps. What do you want to do with data? You want to read it from a database and from a file system, and then you want to do some filtering on each data record, and then you want to join your data. I'm just explaining what's going on in this graph. Then you join your data, you group it, and you write it out. So this is a very typical direct acyclical graph. And looking at it, pretty much everyone should be able to understand what is happening to your data. Compare this to a MapReduce setup where this is extremely not obvious to a non-technical person. Now, moving over to streaming. So far, we've talked about streaming, and I'm explaining how all of these technologies came together and became Cloud Dataflow and Apache Beam. On the streaming side, some of the smarter analysts, they predicted, we think that by 2025, about a quarter of all the data that gets created on this planet of Earth will be real-time in nature. Now, I need to decode what real-time means. Real-time means it is the most valuable if it is processed and analyzed close to the time it was actually created. So that's what it means real-time data. If the value of the data is the most if you process it immediately after it was created or shortly after it was created, then it has a real-time nature. And so IDC, the analysts in question, they predicted by 2025, a quarter of this data will be streaming. Streaming data will be growing twice the rate of non-streaming data. So there's a lot of need and opportunity. Now, for those of you who raised your hands when I asked about streaming analytics, you're probably familiar with the big issue in streaming data, which is late arriving data. What this means is, typically, when transactions get created in your databases, when sales happen on your websites, or when users click on web properties, there's a business element time associated with it. The time of the sale, the time of the click, a business time. Now, unfortunately, there's always a delay between the actual business transaction and the time this event enters your processing pipeline. That's what's called processing time. Because of this delay, it's actually quite difficult to do good analytics on streaming data. What customers want to do is group and do analysis on event time dimensions, on business transaction dimensions. They don't want to do analysis on processing time. Now, Millwheel, the paper that we published in 2012, 2013, solved the problem of determining how to massage your streaming data and create tracking mechanisms for when to kind of decide, yep, now I have enough data to make a decision for event time. So this paper became the basis of a lot of streaming technologies, including Dataflow. And one important concept that was introduced in that paper was watermarks. Watermarks is what solves the issue of late arriving data. Now, going over to practical things, what can you actually do with these concepts and ideas? In the Google Cloud, you would probably build a streaming pipeline or streaming system using the technologies on the slide. And I try to visualize them in simple steps. So the first step is usually ingestion of data. And you can use a service such as Cloud PubSub, which provides a PubSub-like interface. You have publishers, you have subscribers, you have topics, you have subscriptions. Publishers push data into topics. Subscribers read from subscriptions. Very simple, hopefully. Then, after you ingest the data, there comes the step of aggregation, enrichment, lookups. And this is where we have the Dataflow service available here. Dataflow provides, in streaming mode, the aggregations by time, the enrichment capabilities for your streams from PubSub. Now, once you enriched and analyzed and aggregated your data, there comes a point where you want to either save your streaming data into a data warehouse and then do all of your further analysis in SQL, or you want to connect your events with machine learning capabilities. And for that, we have Cloud AI platform. For data warehousing, we offer BigQuery. Who of you have heard of BigQuery? Okay, quite a bit of you. Yeah, BigQuery is very popular and a powerful technology that a lot of customers are starting with in the Google Cloud, and then they use more services as they go. We also offer Bigtable, which provides a NoSQL interface, reads, writes for larger records, but very fast. So the benefit of Bigtable is you can write and read really quickly. Now, in every stream, there's always a little bit of batch. There's always a need to either do historical onboarding of data, or perhaps you need to correct your business logic and reprocess a stream. So for that, Dataflow offers the same capabilities, but in batch mode. And one of the great things about Cloud Dataflow is it offers the same API for both streaming and batch, so that you don't have to learn different sets of skills. You can use the same code in streaming and batch mode and achieve the same processing results. Batch will run things cheaper, but streaming is real time. Lastly, we also have an orchestration service called Cloud Composer. I mentioned Beam and Dataflow. Let me quickly show you the differences between the two. Beam is the Apache Beam project, the SDK. So this is the equivalent of Spark or Flink. It's one of the top projects. If you look at the Apache website and the published statistics, there are a lot of developers who are communicating and trying to learn about Beam and also contributing back to the code base. So it's not just Google that develops it. There are many others who contribute. It offers this unified batch and streaming concept. And one of the key things about Beam is portability. No one else has it, and this is a unique property of Apache Beam. I'll explain a little bit more what portability means in this context. Now, Dataflow is the managed service. It is a serverless managed service, meaning you don't have to worry about clusters. You write these direct acyclical graphs of data processing steps. You submit it to our service, and we determine how many resources to create, how many virtual machines, how much storage to allocate. We'll scale it up and down. We'll really try to optimize your costs, minimize them, and execution time also, reduce the execution time. And we also offer, the last bullet on the slide, a very cool technology that separates state storage from compute. I'm going to talk a little bit more about in the following slides. About Beam and portability. You can think of Beam's portability promise as portability across languages and portability across execution environments. So the goal for Beam is the Beam project, the Apache Beam project, is to provide the same capabilities and APIs, such as a summation by key. So it's a very typical operation in data processing. You need to sum something up by keys, right? If you are familiar with SQL, select some field name from table X, group by key, right? So this capability, everyone needs it, And we are offering it across all of the languages that we support: Java, Python, Go, SQL. Now, once you have this pipeline written, you can go and run it. And where do you run it? Well, you can run it in Google, the Google Cloud. That's the first runner. But you can also run it on-premises or other clouds using existing data processing frameworks such as Flink, Spark, Apex, Gearpump, Streams, Samsa, etc. So we have what we call runners for each of these distributed frameworks. And you're able to run the same code on each of these technologies without any change. So now I wanted to transition over to sharing some lessons that we learned by building the Cloud Dataflow service. And I wanted to start first with the first lesson, which is you can achieve great scalability results if you separate state storage from compute. Let me explain what it actually means. So if you look at the traditional data processing architectures that underpins many of the existing data processing frameworks, Spark and others, you have virtual machines that run user code in parallel. And these virtual machines typically have network-attached storage, the equivalent of disks. And all of these machines communicate through a network. And there's a control plane. So the top layer is called the data plane. There's a control plane that manages all of these data plane VMs. Now, the traditional design works really great for any sort of parallel data processing, except when you when you have to do joins and groups. When you really have to bring data together that is presently distributed across different workers. Whenever you have to bring data together, once you go into terabytes and perhaps petabytes of data set sizes, you run into trouble. And here's why. Who of you knows what shuffling is? Well, I'm impressed. Many of you do. So in shuffling, what you want to do is you have a distributed data set. So you divided the input data set into, let's say, kind of unsorted key value pairs, and you collocated them or distributed them across workers. And you want to actually, when you do a grouping or a join, you have to have the same values associated with, you have to have values associated with the same keys on the same worker so that you can actually join or group by them. So you end up, you as the data processing framework, you end up doing a lot of data movements. You shuffle data from one worker to another worker. There's a lot of data exchange going on. And you end up with sorted data sets where each worker owns particular keys or key ranges. So this is shuffling. Now, as you can imagine, once your data set goes into dozens of terabytes, maybe hundreds of terabytes, this process of trying to shuffle all these key value pairs across workers on a group or a join can basically bring your network down. So we developed a backend service that works almost entirely in memory, although there is a offloading capability on disk as well. And we call it Shuffle, Dataflow Shuffle, very original. The way it works is you don't have to change your code of the pipeline, of your data processing pipeline. You just give us a parameter and tell, look, I don't want to do the shuffling on my workers. I actually want to do it in a backend service. And so we will automatically arrange resources. You won't have to deal with it at all. We'll take the code of your pipeline and we'll run your user code on the virtual machines. This is your compute cluster. But then the shuffling piece will be done entirely in a backend service. And the way we implemented this backend service is we deployed in each Google region and each availability zone at Google, we deployed a copy of this service. And in each of the zones, we have a distributed file system that works mostly in memory, but also has offloading capabilities to disk. Most of the time, data gets entirely sorted and shuffled in memory, so it's much faster than the previous architecture. but we also support much higher data sets than before as well. So here's some statistics on real pipelines we ran. Some of our customers reported they saw a reduction in processing time for these large grouping and joining operations, 5x reductions. They also saw the ability of our service to scale up to hundreds of terabytes by switching to Dataflow Shuffle. Again, you don't have to change your code. This is the benefit of a serverless service such as Dataflow. It's only a parameter that you need to set, and we automatically start optimizing the resources for you. Now, we talked so far about batch processing. How about streaming? Is the same need present in streaming pipelines? The need for storing state and doing shuffle? The answer is yes. Streaming pipelines too have to do grouping and joining. But in addition to grouping and joining, streaming pipelines also need to store window time elements. And I will connect it to the slides I showed before. Remember the chart that explained event time and processing time? Now, in order for us to give users the nice ability of do analysis on business time dimensions, on things like sales time, sales transaction time, or the click time, instead of the timestamp when the record enters the pipeline. So in order for us to provide this ability, we need to buffer all of these time elements and wait until we know that a window has closed. There's a term, closing the window. We have to get triggered, and we have to close the window, and only then can we run a processing operation on it. So it turns out that in the traditional architecture, in a streaming pipeline, in addition to saving all the shuffle data, you also have to save all of this time window data. And it gets stored on workers. And so when the process comes of either closing windows or when you have to bring the shuffle data together, there's even more intercommunication between these workers. Very difficult to scale. Now, we also released a tool called Dataflow Streaming Engine, which is a backend service that replaces this communication on the worker side. There's basically no storage anymore going on your virtual machines. All of the storage is happening in our backend service. Think of it as a database of state. So we have a database of state. And this approach allows us to better support you, but the main benefits is scalability. Let me actually explain why scalability is working better with Streaming Engine. I'm comparing two architectures here. So I'm comparing the architecture without the Streaming Engine and with. When you don't have the Streaming Engine and you have to do the shuffling and state storage on each individual worker, your unit of scale is workers. So you have to scale CPU and storage simultaneously. You're very fixed and very inflexible in scaling the resources. Now, when you have Streaming Engine, you can scale your compute resources independently, and you can scale your state storage independently. So if you have a very compute-intensive pipeline, you as the service can create a lot of CPU resources. But if you have, let's say, proportionately more state storage, you can scale the Streaming Engine a little bit more. So here's a comparison of two real pipelines that do the same processing, kind of run the same code, one again with the Streaming Engine and one without. On the left-hand side, we have the Streaming Engine. On the right-hand side, we have the traditional architecture. I'll start with the bottom chart. The chart shows you three metrics. How many workers we created? Workers mean virtual machines. So how many workers we created to process this workload? The middle graph shows you the CPU utilization averaged across all workers. So it's the average CPU utilization. And the bottom chart is the throughput of your pipeline measured in megabytes per second. So I had a workload that created a bunch of records and inserted them into PubSub. And just look at the things that are happening at the bottom, right? So this is the throughput. I was getting about 50 to 60 megabytes per second into my pipeline in both cases, both the left-hand side case and the right-hand side case. Actually, with the Streaming Engine, I had more. Now, the scaling happened like this. In the streaming engine case, we scaled to about 100 workers, then we went to 150. In the traditional architecture, we went all the way to 150. And our CPU utilization, look at the CPU utilization. Our CPU utilization in the streaming engine case was high, which is good. It was about 80%, 80 to 90%. While in the other case, it was maybe around 70%. So this means you as the user, you actually saved some resources because we didn't have to scale all the way up to 150 workers at the beginning of the pipeline. The other benefit, just watch what happened after my workload stopped. The streaming engine pipeline immediately descaled resources and went all the way down to 1 worker, while the traditional architecture had multiple steps of downgrades. There's a reason why this step thing happened. It's because of the tightly integrated state storage and compute. Actually, in traditional architectures, the way you scale state is by reassigning disks. And as you can imagine, reassigning disks takes a while. So you have to scale down a little bit, reassign disks, scale down a little bit, reassign disks. And this is why you see this step function. Again, you as the user, you benefit from not having to pay for all of the workers being run pretty much without good reason. CPU utilization in the streaming engine case was high again in the 70%. I'll just pause and let you think, why do you think the CPU utilization kind of varied a little bit or went through, was very choppy in the streaming engine case? I'll explain. We only had 1 worker, and we just represented the CPU util of 1 worker. While if you look at in the traditional architecture's case, the CPU utilization was low, around 10% for a very long period of time. That's wasted resources. So hopefully I was able to show you that using the separated state storage and compute approach saves you resources, it improves auto-scaling, it's a much better technology and approach. Now, some of you might think streaming is really hard. I just heard 15 minutes Sergei talking about streaming engine and how things scale up and down. This is really hard. And it is for some of the users, or actually many users. Creating a nicely and finely tuned streaming pipeline is not easy. That's almost an art. So we set ourselves the goal of making streaming less difficult, almost as simple as batch processing. And one realization we had in this journey was, look, knowing Java and Python and Go is great, but the majority of the data engineering world knows SQL and is quite capable of writing great pipelines using SQL. So why don't we extend SQL and offer the same capability for joining and grouping as in the relational world, as in batch world, but let's extend SQL with streaming extensions. Let's allow SQL to express this time windowing concepts. And that's exactly what we did, and we went actually beyond that. We embedded the Dataflow SQL capability right in the BigQuery UI. And so we made the same SQL compatible with both BigQuery and Dataflow. Now you can use BigQuery for running analysis on your static data, and you can use Dataflow, same SQL dialect, to run analysis on streams. And here I wanted to show you a demo, and in the demo I'm going to take a stream, a pub/sub stream, and it's routed through, it's a stream of transactions, sales transactions, your typical data such as the product that was sold, the person who purchased it, and the place where it was, where the product was sold. And so I'm bringing this together with a lookup table. So I need to enrich my stream, and I need to look up the sales region of that sale based on the location of the sale. And since this is a US-based example, I'm actually going to do the lookup through the state. The US state have a table in BigQuery that stores mappings between states and sales regions. So now, after I brought the static data with the streaming data together, I'm going to do a grouping by the sales region. And the end result will be a statistic for my sales managers. In each of the regions, they will see a dashboard of how much sales they're making every 5 seconds. It's going to be a real-time dashboard. They'll be able to track their sales near real time. So let me show you how this all works. I told you previously that we integrated the UI for Dataflow SQL into the BigQuery UI. For those of you who are familiar with BigQuery, you'll recognize this page. The only thing you need to do to actually go and switch to the Dataflow mode is by going to Query Settings and choosing the Cloud Dataflow engine. The main area here is where you type in your SQL query. On the left-hand side, you have a navigational bar, and then you have some history for queries at the bottom. Now, in addition to supporting SQL, we also support schemas of streams. And this is how you can check the schema of your pub subtopic or my pub subtopic, the transactions topic. My transactions have attributes such as, and they're all in the payload attribute. They have business attributes such as the transaction time, the first and last name of the person who made the sale, as well as the location of the sale, city and state, the product that was sold, and the sales amount. Okay, so this is the schema of my stream. Now remember, I wanted to map it and look up the sales region based on the state. And here's the table in BigQuery that gives me this mapping. It's very simple. It has state codes and sales regions. Here's a preview. If you're familiar with the states in the United States, then let's say the state of Missouri is mapped to region 1, and then South Carolina is also region 1, and Vermont is region 2. It's quite simple. Now let's go and write this query. I am a bad typer, and so I'm going to pull one of the previously ran jobs and just reuse the query I ran before. It's all saved in the job history. Here's something that I ran just a few hours ago. I'm going to reuse it. Here's my query. Let me explain what's going on here. I take my pub subtopic, that's my transaction topic. I'm joining it with my BigQuery table on this field, and then I do a grouping. And this is where the SQL starts differing from the standard SQL. Right, this tumble window is only streaming, only available in streaming extensions. The concept of tumbling windows means you are dividing your data records into time windows based on some time attribute. Now, in the projections part of the SQL statement, I'm going to generate statistics for sales regions. And I'm going to insert the timestamp of the beginning of the time window, and I'm going to do my analytical function, the summation of all the sales. So I'm done with my SQL query. Let's go and actually run the job. Dataflow will ask me, what is my destination table of this export data set? And I'll mostly use the predefined settings. And within a second or two, I will get a job ID for my Dataflow job, which will be populated in a minute or two. I didn't want to spend the time waiting here doing the demos. I actually ran the same query just an hour ago before the demo. Here's what you would see after you waited for the Dataflow job. It's very simple on the top level, but if you open up, you should be able to recognize your SQL statement. Because you have this is a director cyclical graph, right? So what I spent earlier in the presentation talking about, this is the DAG. It connects, every business transform is connected through edges. Here's my branch that does reading from, let's actually see. This is my BigQuery branch. And as you can see, input, BQ rows. And this branch is the reading from the pub substream. Both inputs get joined in my pipeline. I also have a aggregation step. This is my summation by a certain combination of fields. So grouping, windowing, that's my windowing operation. This is my grouping operation by sales region. And at the end, I'm writing my outputs, and I'm writing them into a BigQuery table. Now, you might ask, Sergei, proof that this thing actually works. So this statement reads from the table that the previous pipeline was writing to. And check this out. Pay attention to the timestamps of the records that the query prints. Again, pay attention to the most recent output. So the timestamp is 14:25:20 UTC. If I run it again, it now changed to 35. So every 5 seconds, the SQL statement emits new records. Instead of being a snapshot of data, now you have a living and breathing pipeline that creates it. Great, so this was my demo. Hopefully it was illustrative and demonstrated the power of streaming analytics and Dataflow and PubSub and BigQuery. Just to quickly summarize, Google Cloud has a lot of options for you today, both for infrastructure as a service as well as specifically for BigQuery and streaming analytics. We showed how separation of compute and state storage was really helpful with saving resources and reacting faster to changes in the workload. And we also saw that SQL was a great enabler for streaming analytics pipelines. At this point, I would like to take questions. I think there was, do we have any questions from the audience?
Yes, we have.
Great.
Thank you for this interesting report. The first question, are there any similar products in Amazon or Azure? If yes, what are advantages over them?
The other cloud providers also have similar products. In the Amazon world, Amazon has Kinesis Data Analytics and Kinesis Streams. This is their streaming analytics targeted offering. And in the Azure world, there is the Azure Stream Analytics, they actually call it, or event analytics or Stream Analytics. So they have a similar product set there as well. I recommend you checking out a recent Forrester report on streaming analytics. It's quite illustrative and quite informative. It compares all of these vendors together, and you can learn more about other clouds, on-premises, and how they compare with each other.
Thank you. The next one. Are there any plans to have a Scala API for Apache Beam? Because boilerplate of Java for data processing API can be blocker for some organizations.
All right, so here we have an example of someone actually using, well, deep into Apache Beam. So the question was about, do we have a Scala API? The answer is yes. It's actually provided by one of our largest users, by Spotify. Who of you is using Spotify as a user? Okay, some of you. So when you use Spotify, all of this data gets through Dataflow into BigQuery, by the way. All of your playlists and all of the great recommendations you get there. So Spotify is a big user of Dataflow, and they created their own library for Apache Beam. They call it Shio, and it's the Scala API for Beam. Now, I also wanted to touch upon the Java boilerplate part of the question. Accepted, acknowledged, not a good thing, so we improved it. We added recently support for schemas across all of the language versions of the SDKs. And with schemas, there is no boilerplate. Check out schemas and filters. Because with both of these technologies, what previously was maybe 20 or 30 lines of code is now 5 lines of code. The language is very natural. You write things like group by, field name, filter by, X, Y, and Z.
Okay. Can Dataflow shuffle still be efficient without a petabit network connection?
The petabit network connection is not the connection that you need to have to our data center. This is the connection between our components. So I think the answer, maybe if you were asking, is the network really the enabler? It is the enabler. You do have to have a fast network. Now, as a customer, you actually don't have to worry about because all of this is happening in our data center. If you wanted to build your own shuffle service, then my recommendation would be to find a place that has a fast network.
What is the largest meaningful time window for streaming data?
If the question was what was the largest window of time a streaming pipeline can support, we typically recommend customers stay in reasonable bounds, maybe weeks or months. We do have customers who are trying to do year-long windows or even global windows. That's okay. The technology can scale, but the consequence is your pipeline really becomes a database. So you save everything in the pipeline. Your window never closes. So you just trigger on conditions and do calculations, which is awesome, but you will be saving a lot of data in this backend service.
Okay. Do you collaborate with Calcite and Flink communities to define a scale streaming dialect?
Yes, we work together with Calcite, Apache Calcite, which is the Apache project that kind of defined the streaming extensions. We have a flavor of Dataflow SQL that uses Calcite SQL. And we are definitely working closely with the Flink community on the SQL. We actually co-wrote a paper with them on streaming extensions, trying to standardize the streaming extensions for SQL across all of these distributed data processing frameworks, including Flink, Calcite, and Beam.
Thank you. Does Dataflow is similar to Apache and NiFi?
I think both Apache NiFi and Apache Beam / Dataflow can be used to address and solve similar use cases. But there are differences as well. And there's actually, if you Google compare NiFi with Beam, there's a page that shows you the differences. Exactly once processing is one of the main differences. Beam and actually Dataflow together with PubSub, we have a tight integration with PubSub. The combination of Dataflow and PubSub offers you exactly once processing, which is a big deal for practitioners of streaming analytics and streaming processing. It's not easy to build exactly once, but it gives you a lot of benefits.
Thank you. How many developers are working on Apache Beam internally in Google?
Internally at Google, I cannot tell you, but I can tell you that 500 people across Google and other organizations contributed to Apache Beam this year. And we have around 65 committers in the project, which is a pretty large number. It's a similar number compared to Spark and Flink.
Mm-hmm. The next one, what kind of tools are available to measure performance of queries?
Let me try to repeat the question. What kind of tools are available to measure performance of queries?
Yes.
Okay. So we do have profilers, and this is actually something that is available to you today. You can export your profiles, job profiles, and use them in Stackdriver Profiler. There are instructions on our docs site to show you how to dump profiles and load them into Stackdriver Profiler, which many advanced customers use. But we're also trying to improve our support for Stackdriver profiling and other tools, and so you should see more features coming out here in the future.
Thank you. And the last question is, are there any rules to evolve streaming job state in case of the job evolution? if yes, is it the same in the case of SQL API?
If you don't mind, can you read the first part of the question?
The first one. Are there any rules to evolve streaming job state in case of the job evolution?
Okay, so are there any rules to evolve the stream state? Most of the time, when you write your streaming pipelines, you don't have to worry about storing state, evolving state. We handle this for you. You really write just this DAG, and we handle all of the state processing for you. Now, there is a way for you to manage your own state in the pipeline. There's a state API in Dataflow and Beam. And so for that, you can actually do pretty cool things with it. You can, for example, calculate and store counters by key. Perhaps one lesson for you, or one pattern, or one recommendation is state needs to be by key, because this is the only way for us to parallelize the storage of state. We always parallelize by keys. So think of how to, what's the most natural key for your streaming pipeline? Is it a customer ID? Is it allocation code? So kind of think of what the natural sharding mechanism, keying mechanism is for your pipeline. That would be my biggest recommendation.
Okay, we are out of questions. Maybe someone wants to add their questions from the audience? No?
And I would be also happy to talk to you afterwards in this little pre-podium place. Thank you so much. Appreciate you coming here.
Thank you.